All right. Is that good? Can you hear me? No? Hang on. How about now? Yep. All right. Hello, everyone. My name is Declan Andrew. I'm from the University of Edinburgh up in Scotland. I'm working on my topic called Understanding Earthquake-Induced Damage and Healing of Crustal Rocks. I'm doing this with Mark Chapman and Andrew Curtis. And as we'll see, this project ties in quite closely with what Manuel was doing and also with Ziwa, who will be presenting tomorrow. So I thought I'd give a quick overview of what I want to be doing with this project, as well as the experiments that I'm trying to set up and understand. So a quick background about this topic. As Roel pointed out on Monday, there's a lot of observations of seismic waves propagating through the Earth that have been observed to temporarily deform rocks, causing them to soften. And this is shown in their change in seismic velocity and the change in arrival of seismograms. These weakened rocks are then observed to heal over time, so they recover their stiffness over different timescales of minutes to years. And while there are lots of different numerical models that describe these processes phenomenologically, there's currently no consensus on what physical processes are occurring that cause this sort of healing effect that we observe. So in order to investigate this, my objectives to sort of get to the bottom of how this is occurring is I want to observe this recovery of seismic velocities in sedimentary rock samples within the lab in Edinburgh, which I've already started and getting into some codawave interferometry. I want to take these samples and use a pump and probe method, which is also known as dynamic acousto-elastic testing, to try to figure out some basic numerical models that I can use to build upon to create more physical models by measuring the change in moduli with differences in strain rate. Finally, I want to use a cool apparatus we have down in Edinburgh called Mjolnir. And what this does is it is able to take some really cool 4D X-ray or do some 4D X-ray microtomography, so capturing images of changing in the pore structure over time, and sort of compiling all these together to create a better physical model that we can use. So a couple weeks ago, in a mild panic to find some results that I could show to you, I went down to my lab and basically whacked some rocks for a few hours and tried to capture this sort of healing process that we talk about a lot. So I had just some Berea sandstone samples, put a steel plate over them and just basically just hit them with a hammer. It's not the most repeatable of experiments, but it gets the job done. I put some transducers on them and just basically surveyed them for an hour. So I did a survey about every minute for about 60 minutes and measured the coda waves. So what we're seeing here is in microseconds. So this is towards, each waveform was about 400 microseconds long. So we're sort of in the coda wave territory here. And while I did 60, I've shown 12, otherwise it's a bit condensed. So each line is about one survey every 5 minutes. So we're starting with the blue line and going sort of down across the peaks. I know I could have picked a different color bar, but here we are. As you can see, kind of already just by the naked eye, you see there's a bit of a sort of a power law or a logarithmic decay in this velocity change over time. And then after about an hour, I surveyed it again for about 30 minutes. And we see that these velocities have basically fully recovered. Also going off what Celine was saying yesterday with these, this scattering of waves, you can kind of see these little lumps and bumps appear across the coda waves, which sort of shows how these waves are picking different pathways as the rock begins to heal over time. So just on like a first order peak-to-peak difference, just on this time window, there's already, you can see like about a 0.29% change in the velocity. So I want to use this data and do some coda wave interferometry on it, which will be basically what I'll be doing once I get back. I also wanted to use the dynamic acousto-elastic testing method, which allows you to measure the changes in velocity over different parts in the strain field, So I'll be heading over to Newfoundland to do some of that, just to create some basic numerical models to build upon. If you have, can you see that? Oh, yeah. So in any sort of linear material, so if you had like a aluminium sample, as you change the strain, your change in moduli would be just like a straight line. But in these samples of sandstone, as we have this sort of lag time of recovery and stiffness of the healing, we end up getting these different pathways of recovery where we get these cool sort of hysteresis loops. And then finally, I wanted to talk about Mjolnir. So this was the apparatus we have in Edinburgh, and I think Ian will be giving a good talk on this on Friday. This is a setup that we have that can be used under pretty extreme pressures and is also able to capture these changes in the pore structure or like these microfractures at a good resolution. So if we can capture this while the sample is recovering, I think that'll give a good insight into the physical processes behind healing. So yeah, in conclusion, what I really want to do is sort of fill in this gap between observed seismic velocity recovery, the numerical models that go along with it, that Christoph and Snyder and Roll have done a lot of work on, and then link that with observed physical phenomenon that we can actually see. So, yeah, that's all for me. Thank you.
Thank you.